9, or read Robert Lang's book, Origami Design Secrets. And basically it lets you fold things like high level. And a key component of it is to pack disks into a square. The square is your piece of paper. The disks limbs of your creature, and you can't use the same piece of paper to represent this limb and this limb, so the disks have to be disjoint. So it's all about packing those disks into a given square, and yeah, so that's at a high level why we care about disk packing. And people have thought about disk packing a lot, but surprisingly it hasn't been proved hard until 4 years ago. So, this proof is also complicated. So, it involves a lot of geometry and trigonometry and some calculus and fun stuff. So, I'm going to give you a sketch of it. It should be believable that this works, but the details, again, are messy. For starters, let's say that we're packing disks into an equilateral triangle. This is much easier to work with. I'll go to a square in a second. So if I have this equilateral triangle, what I'm going to do is first I'm going to give you a bunch of disks that are forced to pack in this nice triangular grid arrangement, leaving these dark holes. And I'm going to give you more disks, and so the more disks have to go into those holes. And these are actually kissing disks. They're touching. So you can only put, every disk you put from now on will be in one of these holes. And I'm just going to do this big enough so that I have at least n/3 holes. Each hole is going to represent a bin that I'm trying to put a triple of numbers into. And then here is the construction for, I guess this would be a 3-partition gadget. We want to get that, so I type it out, AI plus AJ plus AK is less or equal to T. And so these are the 3 disks representing AI, AJ, and AK. And there's an extra disk in the center. And what's drawn here is everything is maybe tight, almost as touching. But we're going to shrink these disks a little bit, or rather, I'm going to shrink, yeah, I guess I'll shrink, well, that's right. I'm going to shrink this disk a little bit, and I'm going to make these ones a little bit bigger, according to the AI values. So this one will be proportional to AK larger than the disk that would perfectly fit here, if this one was maximally sized. And so that's going to force this guy to move away. Well, he's a little bit shrunk, so maybe he doesn't have to move away. But the center disk, when it's shrunk down, it has a little bit of flexibility. It can move more this way. If this disk is smaller, it will move more this way. It can move more this way, more this way. And in general, you show that these guys are sort of placing demands by being a little bit bigger. They need to push out. And this one is a little bit smaller, and its size is just a function of T. And so it's going to move around. And the claim is it has a valid position if and only if AI plus AJ plus AK is less or equal to T. I have written down a little bit of the details. So we're going to choose some big number, capital N, maybe it's like n to the 100, little n to the 100, something like that. And we'll shrink the big disk by that amount. I'm going to scale everything so that T equals 1. That will simplify things a little bit. So just shrink everything, all the values down, divide everything by T. AI is in the T. And then I think we're going to shrink the AI disk by -1/n squared plus AI over n. This is a funny notion of shrink. I'm going to first make it smaller by 1/n squared, and then I'm going to grow it by AI over n. This term, I believe, is to get rid of smaller things in the Taylor expansion. So disks are annoying because they're circular, because they're quadratic curves. And so you get it's an awkward shape to deal with. And you're worried about how I move this center relative to how I move the other centers and whether they're hitting each other. And whether they're hitting each other is a quadratic constraint. You have to measure the distance between these 2 points. It should be greater or equal to the sum of the radii. So that's tough to work with. So to simplify things, we take first derivatives and say, well, to the first order, what's happening when I move these disks around? And when you take first derivatives, you get an approximation to the truth. And the second derivative, it tells you a little bit more of the truth. And if you've ever done Taylor series, you know you get something like 1 over n, something times 1 over n plus something times 1 over n squared, and so on. And so if we just subtract off this term, make these disks a little bit smaller than they need to be, that lets you deal with all those terms all at once. So it lets us focus on the lead term. And to the first order, the claim is, what happens is, well, we made this disk smaller by 1. Remember, 1 is t. We made the other guys larger by ai. So that's going to work out exactly when the sum of the 3 i's is less or equal to 1. Then this will all have room. And that's true to the first order, and you have to do this ugly business to make it true exactly. So I think, without going into vector algebra, this is the intuition of what's going on. And that's that proof. Any questions? The point here is to expose you to lots of different ways to represent numbers and 3-partition. And a lot of the times it comes up in geometric settings, but so far we've seen rather different ways to represent it. We'll see graph theory in a moment. Probably next up is games and puzzles. So let's play some games. Right. There was one more part of this proof I forgot. What if you're packing into a square? This is particularly important for origami. This paper appeared in an origami conference, so we needed to solve the case of square packing. This is more awkward. The idea, because you can't make a nice regular grid on it, square grid packing is not very efficient for disks. But if you have these 4 really big disks, I should mention here the goal is for the disk to fit, the centers of the disk to fit inside the square. That turns out to be the right constraint from origami perspective. So we make these 4 big disks, they have to be at the corners. Then we make this big disk, it has to be in the center. These are all perfectly touching. Then we add these 4 disks, and it forces a particular arrangement here, which is a little awkward to compute, but you can. And yes, so we do that 4 times. Then for each of these constructions, this is the shape that we want. We want these kind of equilateral triangle-ish gaps. I say ish because they're not straight sides, they're arc sides. But it is the centers form an equilateral triangle perfectly. Then we recurse. So wherever we have a gap like that, which is this thing, then we add this center guy, and then we add these 4 disks again, just like over here, 3 times now. Of course, we can't force the disk to go here, but they will. This is a very symmetric construction, so we're going to do this symmetrically in all the things. The other challenge is we left these rather large gaps here. I mean, relative to these tiny disks, which will all fit inside that gap, this is pretty big gap. So we also have to make these gaps unusable by adding a maximal disk and then adding maximal disks and just recursively adding maximal disks until the gaps that are left are tinier than all the ones that we're going to produce in this recursion. This recursion has depth like log n, so we get, in the end, we get roughly n of these things, or n over 3. If we have extras, we'll just throw in maximal disks and make them unusable. So that's it. So this is a lot harder because you have to fill in all of these gaps and make sure everything is going to be happy and no disk can go in the wrong place. But if you sort of do it in the right order, you can be convinced at every stage your disk has to go where you're putting it. Except at the very end where you have freedom, the freedom you have is where the AIs go, which pocket they belong to. That's the only freedom you have, it's the only freedom we want you to have. Okay. So that was disk packing. Next is Clickomania. How many people have played Clickomania? A few? Good. Not completely obscure yet. So here I have the real thing. I think this is called Clickamania Next Generation. And I want to start a new game so I don't have a really bad score.